Hello everyone. Today we will be continuing our discussion of financial math with a discussion of compound interest. Now in the last video we talked about simple interest, which is basically where you are paying interest on just the principal or the original amount of money that was borrowed. Compound interest is a little bit different from that. The key difference is that with compound interest, instead of just paying interest on the principal, we are paying interest on the principal plus all previously accumulated interest. And that interest can be added at all kinds of different intervals. It can be added annually, quarterly, monthly. It could even be added continuously, as we'll see in a minute here. So when we are dealing with compound interest, there's a few different formulas that we can use to figure out what our final value is given the term, the interest rate, and the principal. So the first one of these we have is for annual compounding. So in this case, our final amount F is going to be our principal times 1 plus R. As mentioned in the last video, R is basically our APR, our annual percentage rate, which is our interest rates. And in this case, when we have this lowercase r, we're expressing it as a decimal. And then T lowercase, that's our term, and that's going to be in number of years when we're dealing with annual compounding. All right. A more generalized version of this, we can just call this the general compounding formula. And this looks basically the same as for annual compounding, except instead of R, our APR for our interest rate, we have this lowercase p. This is what we call the periodic interest rate. Now, the periodic interest rate is basically just our APR divided by however many times we're compounding per year. So say we're compounding quarterly, our periodic interest rate would just be our APR divided by 4. If we're compounding monthly, it's our APR divided by 12, and so forth and so on. And we also have, notice instead of this lowercase t up here in the exponent, we also have this uppercase T. And uppercase T in this case represents the total number of times that compounding occurs over the entirety of the term. Now, the last scenario for compound interest is what we call continuous compounding. And in this case, it's our final amount, F, is P times e to the RT. R and T, once again, are APR and term in years. E is this irrational base that this basically is a number that goes on forever and ever. And so it starts 2.78 or 71828, and then it just keeps going and it never stops. It's kind of like pi, 3.1415926.5, and so forth and so on, right? E is kind of the same way. It's an irrational number, just like pi is. Now, one bit of information that we can get from looking at this formula is that when we have compound interest, the relationship between our final value and our principal over time is going to be linear, versus with the APR and with our term, our total amount of time that we're earning interest for. This is going to be, these two both are going to have a linear relationship with the final value. So, exponential relationship. The principal has a linear relationship, R and T have an exponential relationship with our final value. Now, one sort of effect of this is that over time, if we have the same principal and the same APR, compound interest is going to earn more than simple interest, because not only are we earning interest on the principal, but we are also earning interest on whatever interest has been accumulated up to that point. And the longer we let this go for, the more of a difference it's going to make. So you can see simple interest, the total value over time follows a linear pattern versus its exponential for compound interest. Now, there's a couple scenarios where we'll commonly see compound interest. One of these is with certificates of deposit, or CDs. And this is basically, you can take out a CD from, or with a, a bank or whatever, or credit union, whatever financial institution, you can open a CD. And the idea is you deposit however much money into that CD, and it earns interest, compound interest, and the idea is that you don't touch that money until whatever term you've signed for that CD is over. Typically you can take out the money before the term is over, but you'll usually pay an early withdrawal penalty, basically, for doing that. The other scenario where we'll see compound interest a lot is with just regular old savings accounts. And savings accounts, the nice thing about them is that they are very liquid. You can easily add, deposit or withdraw money at any time. The disadvantage here is that although you are earning compound interest, it's going to be typically with a very low APR. So you're not going to earn much interest on a savings account. So let's look at a couple of examples of compound interest. So the first example that we'll look at, we have an $8,000 CD, and we want to determine the final value after 10 years, and we have a 3.1% APR, and basically we're just looking at different compounding frequencies here. So first one, annual compounding. So this, we're going to use the annual compounding formula right here. F equals P times 1 plus R to the T. So in this case, P, our principal, is $8,000. That's given to us in the problem statement. 1 plus R, so that's 1 plus our APR, written as a decimal. So 1 plus 0.031, that would be 3.1% expressed as a decimal. And then this part in parentheses, we're going to raise to T, which is going to be 10 because our term is for 10 years. And what we get from all of this, so if we do 8,000 times, this would work out to be 1.031 to the 10th. And that's going to give us 10,856 and 17 cents. All right. Now, the next one, we have compounding monthly. So for monthly compounding, this is where we have to deal with our periodic interest rate. So our periodic interest rate is, once again, it's just our APR divided by however many times compounding occurs within 1 year. So in this case, our periodic interest rate is going to be, since we're compounding monthly, that's 12 times per year. So it's going to be our APR of 0.031 divided by 12. So that's going to give us 0.00258. So if we plug this into our general compounding formula, so F is going to be P times 1 plus lowercase p to capital T. This is the total number of times compounding occurs over the whole CD. So this is going to be 8,000 times 1 plus P, we just calculated, 0.00258. And then we're going to raise this to the total number of times that we're compounding over 10 years. So we have 12 times per year, that's monthly over 10 years, so that's gonna give us 120 times that compounding occurs total over the entire CD. And this works out to be $10,903.04. So one thing that you might notice right off the bat is that there's not a huge difference in the final value if we do annual compounding versus monthly compounding. And we'll find that this is also true with continuous compounding. In general, when we're dealing with compound interest, I would venture to say that the frequency of compounding is much less important than the APR and the term in terms of figuring out, or in terms of how much it affects the amount of interest that we're going to earn given a certain principle. All right, last one, continuous compounding. We have this last formula for F equals PE to the RT. So our principal, once again, $8,000. E to the R, and then R is once again 0.031 times T, and then T is going to be in years again, so for this one, so times 10. So what this works out to be is $10,907.40. So hardly any difference at all from monthly compounding. So this concept brings us to what we call the rule of 72. And basically the rule of 72 just states that we can approximate the amount of time that it takes the value of something earning compound interest to double by just taking 72 and dividing it by our APR. And this is the APR expressed as a percentage. And that will tell us the number of years that it takes for the value to double. So in this case, for instance, if we have a 3.1% APR, then 72 divided by 3.1, that would be 23.226. So give or take, it would be roughly 23 years for the value of that CD to double. All right. Now the last example that we'll look at deals with something called the APY, or annual percentage yield. And this is basically just the percent increase in the value of a CD or something else earning compound interest after 1 year, taking into account both the APR and the frequency of compounding. So the formula that we use to find APY is up here, 1 plus R over uppercase T to the T minus 1. In this case, uppercase T represents the number of times that compounding occurs within 1 year. Or in the special case that we're using continuous compounding, it's just E to the R minus 1. Once again, R in this case is our APR expressed as a decimal. So in this case, we're saying the CD uses monthly compounding, so our APY is going to be 1 plus R is 0.031 over T. In this case, T is 12 because we're compounding monthly, or 12 times per year, raised to the 12 minus 1. So this is going to give us an APY of 0.03144 or 3.14 APY. A lot of times, if you go to open a CD, the APY is what they're going to tell. Is what they're going to give you when they're telling you what the interest rates are, or what your what kind of interest you're going to be earning on that CD. Thank you for watching, and as always, I'm happy to help with whatever questions you have.